In this work, we describe a framework for the analysis and simulation of material appearance changes over time due to light exposure. The fading of materials due to light exposure over time is a major contributor to the overall appearance of man-made objects. Real-world materials may lose some of their colors after being excessively exposed to light, with some colors fading more readily than others. Besides providing the viewer with important visual cues, the simulation of these effects also has important cultural and industrial applications. For example, museums are interested in the prediction of long-term effects of light exposure on their art collections, while manufacturing industries are interested in extending the life of surface finishes such as paints and stains. We employed a physical-chemical approach based on the kinetics of color fading processes. Accordingly, the rate in which the material fades over time is determined by the volume of colorant consumed by a given amount of energy impinging on the absorbing particles. This quantity, in turn, is expressed in terms of fluence rate. In a non-scattering sample, the colorant is consumed at a constant rate. While in a highly scattering sample, the rate at which the colorant is consumed decreases with time. In the case of a colorant formed by a mixture of pigments, one component pigment may fade faster than the others. Employing this framework, a layered fading model that can be readily incorporated into existing rendering systems was developed using the Kubelka-Monk theory. For more details, please refer to our article. Several sets of experiments were conducted subjecting different materials to light exposure over time. The selected materials include newsprint paper, two dyes, namely toluidine blue and Congo red, which were prepared for experimentation by immersing newsprint samples into the dye solutions, and cork typically employed in bulletin boards. Using a spectral photometer setup with an angle of incidence of 45 degrees, reflectance measurements were taken before and after exposure. The samples were exposed to a fluorescent lamp, whose spectral irradiance was also measured during our experiments. For the newsprint, to determine its absorption and scattering coefficients, reflectance measurements were taken of an unexposed sample. Although the handling of heterogeneous material samples resulted in some quantitative variability in the measured curves, their dominant spectral trends were fully preserved. For example, the measurements for newsprint indicate the simultaneous rapid fading between 500 and 600 nanometers, and a darkening outside this interval due to the presence of lignin. As it can be observed in the progression of the simulated curves, these behaviors were qualitatively captured by the proposed framework. In the case of the newsprint sample dyed with Congo red, the measurements indicate a pivot point at approximately 600 nanometers produced by the simultaneous fading of the dye and the yellowing of the newsprint. These trends were qualitatively captured by the proposed framework, which also provided similar results for the blue dyed newsprint sample, as reported in our article. For the cork sample, the measured curves maintained their general shape while increasing in value over time due to the simultaneous yellowing of lignin and fading of the remaining material constituents. As it can be observed in the corresponding simulated curves, this behavior was also qualitatively captured by the proposed framework. To illustrate the effectiveness of the proposed framework, we have rendered several scenes depicting typical fading scenarios. In this setting, the fading simulation accounts for the yellowing of newsprint due to the presence of lignin, which resulted in an uneven fading pattern as the newsprint was folded during light exposure. In this sequence, the position and orientation of various pieces of furniture were jittered to account for the fact that these objects would not maintain their exact locations over a light exposure period of many years. Here we demonstrate the effects of light exposure on a painting before and after an extended period of time. Note that the painting is composed of single colorants. Finally, in this sequence, printed materials have been added and removed from a bulletin board over time, resulting in an irregular fading pattern. In this work, we have presented a novel framework that provides the basis for predictive simulations of fading processes.